Okay, can everybody see me? Good. All right. My name's Alan. I want to welcome you all to the Computer History Museum. And I'm going to be the one to tell you the story about this amazing man, Charles Babbage, and his amazing invention, difference engine number 2 behind me. This is Julie down here. Julie is the power supply for this machine. She's going to be absolute cranky because this is a human-powered calculating machine. And it takes a lot of energy to make it work because a lot of stuff happens on this thing, a lot of gears and things moving around. So you'll see that in a minute. So before I even start to talk about this thing, I'm just going to let Julie crank it a few times. And what you guys can do is kind of watch it work and hear it work and watch the printing stereotyping section over here all work, and then I'll explain everything to you. In fact, while she's doing that, you might want to take a quick spin around, but come back to the front just to see what goes on in the back. We'll be going back there later, actually, but if you want to, you can walk around. So let's go. You can imagine what this thing does and why it does it. Walk around. Carefully. First one. DNA? Who said DNA? Yes, okay. Come on back around to the front. All right. So Charles Babbage was born in England in 1791, about 220 years ago. And he was a really smart guy. Even though he was a son of a fairly wealthy London banker, he studied math. He really loved mathematics. And he studied in Cambridge, and he liked to do a lot of inventing. He was very, very interested in many kinds of science. So during his career, not only did he invent these amazing machines, but he invented things like the cow catcher that they used to put in front of locomotives to push cattle off the tracks. He invented a black box recorder for railroads so they could keep track of the speed and distance that the locomotive was going, like an accident recorder. He built his own RV to tour Europe in at one point. He had a submarine design. He was into all this kind of science. Today we kind of call a man like that a DaVinci Man. Very broad interest. Unfortunately, in personality, he was a little bit geeky. He had a lot of trouble communicating sometimes with other people, especially if those people disagreed with him. And he had a lot of problems with that during his lifetime. I'll read a little thing later that will show you exactly what I mean. In any event, the story of the machines begins in the 1820s. In the 1820s, and right up to the 1960s and 70s, the way engineers did most of their work was we had this gadget, a slide rule to do math, and we had a book of mathematical tables. This is actually mine from college 50 years ago. And we didn't have personal computers on our desk. We couldn't do math with computers. So these books contain tables like these things called common logarithms that we used to compute numbers with. It contains trigonometric functions and all these things we needed to make things. Well, Charles Babbage and a friend of his were going through various publishers' editions of these books. Everybody used to put them out. And what do you think they found when they compared the books?
Error.
Maybe there were differences between one book and another. That shouldn't make sense. All these numbers in the same place should be the same, right? So he said, this is really terrible because at that time, England was in the middle of what we call today, if you study history, the Industrial Revolution. There was many machines being built, complicated machines, bigger and bigger buildings, bigger and bigger bridges. And if somebody used a wrong number, it could be terrible. the bridge could fall down or the building could collapse. So Charles Babbage was really horrified at this idea, and he said, "This cries out for steam." What he meant was, that was just a way of saying, there must be a way to automate the calculation of these numbers so there's no mistakes. And he began to draw a machine, which today we call difference engine number 1, because this is difference engine number 2. Difference engine number 1 was a behemoth. It was big. It had 25,000 individual parts. And once he had drawn it out and thought it might work, he needed the next thing every inventor needs to make their invention real. What do you think that is? Money. Money, money, money. There were no venture capitalists around like we have in Silicon Valley today. So he went to the government, which is a popular place to get money. Still is. And he asked them for money and showed him his idea, and they said, "Okay, Charlie, we'll give you some money. Go ahead and build the machine." And he went and found the best machinists he could find, because making the parts was very difficult in those days. We didn't have all these wonderful computer-controlled machines that we have today. So he got this guy, and they started making the parts. Would you believe that after 10 years, they only had about 1/3 of the parts done? 10 years, because there was a whole lot of precision work to do. The government of England was getting very impatient with Charles Babbage, and they called him in to discuss it, and they had a little bit of a fight, because I told you that Charles Babbage wasn't a great politician. He was a geek. And so they told him no more money. And as a result, by the way, he also had a fight with the machinist, who he disagreed with. And to make a long story short, they stopped. They could not make difference engine number 1. While Charles Babbage went right on to design an even more complicated machine, which we call the Analytical Engine. Would you believe it was a complete mechanical computer, not just a difference engine like this. It was a computer. It was programmable using little punched cards. This is in 1830s. Amazing. Well, that was so complicated, that would have been as big as a locomotive on a train. So he didn't get money to build that either. He went on to do other things. But while he was doing that design, he thought of an easier way to make a difference engine. And so he drew that up, but nobody wanted to pay for it. So in his whole life, Charles Babbage never got to see one of these machines work. Now, the drawings went into a museum eventually in London, England. And when they had a new curator of technology in this museum, the guy in charge of the exhibits, he took out those drawings and he said, "Gee, it's 1985 now. I wonder if we could build Babbage's difference engine, and would it work? Was his design correct?" And they started to raise money, and they had also a big process to get this done. In fact, by 1991, Charles Babbage's 200th birthday, they had the machine built from this end, where the crank is, to the end of the calculating section right here. But they didn't have enough money to finish what Babbage thought was a very important part of the machine, the printer stereotyper. Why is that important? Well, the idea was to avoid mistakes. It's just not enough. If you calculated the numbers for the machine and you had to write them down, you could write them down incorrectly. We all have a little problem sometimes with that. And then you hand those numbers to a printer. At that time, the way they made printing was to set little pieces of type, one next to the other, mirror image, by the way. And you could make a mistake setting the type. Charles Babbage didn't want that to happen. This machine actually, after a result is calculated, on this part of the machine right here, it is transferred via these little rods and gears and wind chimes they're not wind chimes, they're weights, and to these type wheels, and it actually prints on this tape the answer. But we won't see that actually happen today. You'll see the printer move, but if we put ink in, it's really a messy job to clean it up. And then in this tray down here, the most important part, you would fill the tray with like plaster of Paris. You know what that is? It's like soft material. And every time the machine gets a result, after it prints it, it pushes the type down into the plaster to make an impression of the answer. And then the tray moves in waiting for the next one and the next one and the next one. When that tray is full of answers, you have a mold. The printer takes it, he pours lead into the mold, and he comes out with a plate, no errors, no mistakes, puts it in the printing press, and prints a page of the book. Question?
Yes, it didn't print the question. Now you have a physical issue of matching up the question to the answer.
You mean what value of X are we working
Yes.
on? Yes, you have to keep track of that. I'll talk about that in a minute. Also, you'll see there's a lot of stuff down at the end here. This stereotype tray has variable formatting to some extent. You can change how many answers you put on a page, how many columns on the page. You know, it's 130 years before Microsoft Word, folks. Now you can do that, and there's two fonts. There's another tray, which is the size of this book. So you can print a big book and a little book simultaneously. Okay, so will the machine work? Well, once the museum had problems finishing this, it came to the attention of a fairly wealthy American named Nathan Myhrvold. He was once the chief technical officer of a little company called Microsoft. And he said, I'll tell you what, museum, I will help to pay to finish the first difference engine number 2 if you will just build me one completely new one for my own collection at home. And this machine behind me, finished in 2008, was serial number 2, the second difference engine number 2, and it's being loaned to us by Nathan Myhrvold. But eventually he's going to want it in his living room. We're going to take it up to Seattle and stick it in his living room. I hope he has a strong floor, because it weighs about 5 tons. But he has a big living room, guaranteed. It's going to go right next to his Tyrannosaurus Rex skeleton that he has already. Okay, so now, what does this machine do? Well, it solves polynomial equations. Now, I know you guys haven't exactly had algebra down in front here yet, but the idea was, if you could simulate this, one of the functions in this book, let's say logarithms, and you could come up with an equation for how those logarithms would be represented. This is just a typical polynomial. You would take, this is a fifth order polynomial, very complicated equation you can see here. You would not want to sit down and solve this equation for thousands of values of x. It would take you forever. So there's a mathematical technique, a mathematical method called finite differences, such that if you solve this equation a certain number of times manually first, you can then use only addition to solve for every other value of x. And I'll show you how that works on the blackboard in a little while. But in the meantime, take my word for it. What you see behind me is just a very fancy adding machine. We put some initial differences, some initial numbers on these 31-digit columns. These we call in modern computer talk registers. We put the initial numbers on these columns. They're called difference columns. There's 31 digits in each column. As Julie turns the crank, we add one column to the next until we come to the answer column over here. Now, to address this gentleman's question, so we can keep track of the value of x and maybe keep track of the stereotype trays, Babbage made it so that we could divide the machine horizontally and do 2 calculations at once. So we're using the bottom digits of this machine by putting a 1 on this column right here. Every time we go through a cycle, it adds 1 to this column over here, so the value of x is displayed right here. And we're currently at 5. X equals 5. Okay. All right. Now, I just wanted to read this to you. You were wondering about, we were talking about Mr. Babbage's personality and why he eventually died without seeing any of these machines work. and I want to read this because it's classic. He criticized everybody, wrote letters to the newspapers. If he had email, whoo, he would have been flaming people all over the place. So he dared to criticize a poem by Tennyson, one of his contemporaries, a very famous poet, take my word for it. He wrote him a letter to criticize one of his poems. He said, "Sir, in your otherwise beautiful poem, The Vision of Sin, there's a verse which reads, 'Every moment dies a man, every moment one is born.' If this were true, it must be manifest to you the population of the world would be at a standstill. I would suggest that in the next edition of your poem, you have it read, quote, 'Every moment dies a man, every moment 1 1/16 is born.'" Doesn't that trip right off your tongue? Iambic pentameter or something? Okay. So anyway, this is why he really never got it done, folks. Anyway, but I want to tell you that this machine was built quite authentically. The museum looked up what kind of metals Charles Babbage had intended to use. It automatically adjusted the tolerance of these modern machines that made the parts so that it would reproduce like 1850s capability and technology, right? So it's quite authentic, and believe me, it does work. So okay, we're going to crank it some more now, and you can watch as the machine rotates these gears to do the addition, and then you'll see the type wheels rotate, the printer will come up to get the impression of the printout, and then you'll see this tray jump in after the impression is made. We don't have plaster in that today. If any of you want to see what a stereotype tray looks like, there's one in that cabinet over there. You can look at it later. Oh, by the way, one important thing is, once this tray is full, you don't want to do any more calculations before you change the tray. So Babbage said, I got to make sure that nobody overflows the tray. So you can, if you look down here, you'll see a little weight. It drops into a little tray that pulls on this piece of cable here that goes across the bottom, comes up here, see it? Across here to a little clutch. And as soon as that tray is full, this will pull and Julie's clutch crank will disengage, will stop. The machine stops. So you can't possibly overflow. He really thought of almost everything. About the only thing he didn't think of was what would happen when you put one of these on a 747 and fly it across the Atlantic. We had a mess when it got here, but we were able to fix it. Okay, so let's crank some more. You watch these things move. Watch the columns, and you'll also hear a snapping. Go ahead. You will hear a snapping noise. That noise. Charles Babbage wanted to make sure that you could never be between two numbers. This is an integer digital machine, if you will. So in order to make sure nothing drifts, these big blades down here go clear up the column. And at a certain point in the cycle, when you want to hold them, it snaps in. You see it snapping in? Bing. And holds those gears and make sure that they're all in line. If you drift it a little, that blade going in will line them all up perfectly. Now here, watch the printing cycle happen. There's a print, stereotype, in goes the tray. Okay. Questions about that? All right, come around the back, folks.
So turning very fast is overclocking.
Was it 5-phase clock?
Okay. Watch what goes on down here. This is really beautiful.
No, actually, it's a clockwise clock.
Okay, what's happening here? Well, you were adding two numbers together, and you start at the right-hand side of the addition, and the number comes out greater than 10. What do you have to do?
Carry.
You have to carry the one or two, whatever it is. You have to carry. Well, so does this machine. If one of the lower wheels is going to go past 9 back to 0, you have to move the wheel one above it by 1 digit, right? What if that goes past 0? Then you got to move the next one. So, as we turn if a number moves past 9, it automatically pops out one of these levers back here. That's called a carry warning. And then at the right part of the cycle, as Julie's cranking, around come these hooks. Starting from the bottom, it looks for warned carries and hooks on and pulls the wheel above it. And that's why they have to be exactly one wheel apart in the cycle. So it goes from the bottom to the top. In modern computer talk, that's called polling a register. We're polling to find out where the carry levers are set, or where flags are set, if you call it computing analogy. Okay? Any questions about that? Okay, now I'm going to step over to the blackboard here. We're going to do a little bit of algebra. So my young ladies here may. Oop. Excuse me. All right, and everybody, if you look over here, I'm just going to show you, for those of you that can remember some algebra, how does the machine work? Well, I'm going to take a very simple algebraic polynomial here. Result equals x squared plus 1. Not as complicated as this guy here. And I'm going to show you how we use the machine. We first have to calculate the equation one more time than this number. So in 3 times, we have to do it manually. If x equals 0, what's the answer?
1.
1. If x equals 1, 1 squared is?
2.
1 plus 1,
2.
2. If x is 2, 2 squared is 4, 4 plus 1 is? Okay. Now, I subtract the first 2 times the energy that Julie's applying now, because the museum put in a 4-to-1 reduction gear. So she would get tired, let me tell you, pretty fast if she was cranking with 4 times the force. It takes skill to crank it because the load on her crank changes at every part of the cycle. So, but she has to do it very constantly. If she cranks too fast or too jerky, something's going to jam in this machine. Things are moving. And you have to have the timing right. We get an answer about every 8 seconds. 8 seconds per answer. For anybody that wants to calculate megaflops. Figure that out. Okay, so there are several things like that in the machine. When they first looked at Babbage's drawing, didn't understand what things were for until they were actually putting together parts. And they went, aha! That's what's happening. It's really tough to diagnose a problem in this printer mechanism if you have to crank it from way down there and have everything moving. So we have a clutch down here. We can throw that lever, disconnect the whole printer stereotyper, crank it from over here, and try to diagnose it. So lastly, the question that I would like to talk about is, what is the impact of Charles Babbage's work on the history of computing? After all, this is a computer history museum. And, there's various opinions about this. You can read lots of books about Charles Babbage, but my opinion is that there's not much impact because he didn't build the machines. Now, had he built them and demonstrated them, there might have been a little more energy devoted to calculating machines. As it was, it went pretty slowly from about 1850, when he quit trying to build this, to the end of the 19th century, where more people were building electromechanical or mechanical calculating machines and then electrical calculating machines. However, I got to tell you that he said, well, we got to get that right. And after that, calculate thousands of values. But yeah, so that's a good answer. So
everybody speculated about that with regards to that.
No, I don't think, nobody ever wants to say right.
Right.
So, but,
I mean, that
Yeah, but
letter is so perfect for that clergy.
yeah. He definitely might have had some.
I mean, it is, you know, like you ask an answer before you say, wait a minute, and then before that, it's 65 seconds.
Yeah. He was a